Good afternoon. This is EC 201, lecture 9. To continue off from where we left, what did we say? To build an amplifier, it obviously doesn't help if you take the MOSFET and hook it up directly to the source and the load. There must be another source of energy. And looking at it another way, we found that unless you bias the transistor well into the saturation region, there is very little hope of getting any gain at all. So in other words, you first set the operating point, okay, which is as simple as putting a battery of value VGS1 between the gate and the source, and a value of VDS1 between the drain and the source. And then we said that the next job was to add the load, and that was done by putting a resistor RL in series with the drain. This is just a quick recap of what happened the last week. So this is RL, and then we realized that obviously the battery of VDS1 is no good anymore because there will be a DC drop across RL. So very good. So we said that's straightforward to fix. We compensate for whatever drop there will be and add it to VDS1. So and we call that new battery VGD. So that's that takes care of the load. All right. Then what did we say? To bias it deep in saturation, which basically means that VDD is going to be much larger than VGS. In which case it doesn't make sense to have another VGS separate battery. One could actually derive VGS from VDD itself, and the simplest way one could do it would be to use a potential divider, and that looks like the following. What is VGS1 now? VDD times RB by RA plus RB, and if you know what VGS1 you want to bias it at and you know VDD, it's quite straightforward to go and figure out what the ratio of RA and RB should be. Please note that this still does not fix the absolute values of RA and RB. Great. And just as an exercise, once you know the VGS1 you want, you can find RA and RB to within a constant, and ID is given by 1/2 mu n Cox W by L times VGS1 minus VT the whole square. Okay. Once ID is known, VDS1, which is the true drain source voltage across the transistor, is nothing but VDD minus ID times RL. Sorry. So in other words, we have finished so far the whole business of setting the operating point of the device. And we'll see later on that there are many ways of setting the operating point. This happens to be just one. And the next job is to add the incremental source. Okay, so this takes care of the operating point. The next job is to add the incremental source. And what did we see last time? We saw that it does not make sense to simply hook the incremental source between this node, between the gate and ground. Okay, because if I did this, for example, okay, so this was Vs, for example. If I did this, what would be the problem? My job is now to add the incremental source without screwing up the operating point. Okay. Now, if I did this, then this doesn't work simply because, we need to find the operating point, we'd set all the independent voltage sources to 0, which means that the gate voltage would be 0, which means that the drain current would be 0 and you're basically not doing what you want. And we figured out that the reason why the operating point, current was flowing into the small signal source Vs was because the DC potential, before we made this connection here, on either side is not the same. So an easy fix for that problem was to in fact put a battery here having a value VGS1. In which case, if this was VGS1 and this was VGS1 before you joined them, obviously once you join them, the potential is going to remain the same. So what we did was this. And then now we come back to the same old problem, which is the whole idea in doing all these antics were to get rid of the battery in the first place, and now we seem to have gotten back to the situation where we have a battery. Okay, so and then we realized that two fundamental things, which are an infinite capacitor charged to a voltage V1 is absolutely indistinguishable from a battery of the same voltage. Another thing also to bear in mind, that a finite capacitor of charged to voltage V1 is equivalent to a battery of voltage V1 provided no current is drawn from the capacitor. So, in other words, the next thing to do is to simply replace the battery by a very, very large capacitor. The source had a source resistance RS here. At the end of last class, some student came and asked me, well, how about this? I was quite happy about it because at least somebody is thinking. This guy's contention was, this is not the only way to add the signal source. Can anybody think of any other way? So you can see that this is another valid way of adding the input. Does that make sense? The voltage at the gate is VGS1 plus Vs, which is what we wanted in the first place. So this is another way of doing it. Okay? However, there is a disadvantage with this. It's not a fundamental disadvantage, it's a practical one. And what is the disadvantage? Well, I mean, look at this diagram here and here. Okay, that's fine. It's not source internal resistance. What else can you see is the difference between the source here and the source here? Source is not grounded. Where? The second case. Okay? It turns out that in a lot of practical applications, one does not have access to both terminals of the source. And one terminal of the source is automatically connected to ground. So you don't have the freedom, for example, to access. If you had both the terminals, sure, you could stick it in series with the gate, as somebody suggested. But in practice, many sources will not allow you to have that. The two terminals floating like this, one will automatically be ground. So while the one shown here, there is nothing fundamentally wrong with it. However, there is a practical disadvantage that both the terminals of the source need to be accessible if you want to stick it in series with the gate. Okay, now another suggestion has come about, which is the following. My friend in the last bench says, how about this? Comments on this one? VS will change, yes, because the operating point will change because there is a DC drop through RS. My friend in the last bench will very legally argue that instead of keeping that original RB, I will make it RB minus RS so that the total thing is still RB. And then your objection about the DC operating point changing goes away. Even then there is a practical problem. One is that, please note that DC current flows through the source. In this chart here, DC current flows through the source, which is again not an option for many sources. For example, this microphone here is what is called a condenser mic. Two plates of a capacitor, and when I speak into the mic, one of the plates vibrates, changing the capacitance between the two plates. And therefore it turns out that it is not possible to have DC current pass through the source. That's just the way the source is built. That is a problem. What do you think is the gain from Vs to the output in that case in this chap? What is the incremental gain? Alright, so what is the incremental gain from Vs to the gate node here, this node? The question is, what is the incremental gain from Vs to that node X? In other words, if Vs wiggles a little bit, X obviously also wiggles a little bit. I want the ratio of this little bit to that little bit. So the incremental voltage at Vx here will be Vs times Ra by Ra plus Rb plus Rs. Vs into Ra parallel Rb by Ra parallel Rb plus Rs. Very good. Okay. So now can somebody make a comment whether it makes sense to use the guy on the top left or the bottom right? Okay, what is the maximum gain you can get from Vs to X? You cannot get anything more from Vs here to X. You cannot get a gain of greater than 1. Okay, and how will this gain ever approach 1? When Rs is very small. If Rs, you have no control over Rs, what can you do to Ra and Rb? Let's say, you have a source, you have hardly any control over the source. So what would you do to make the gain from Vs to X approach 1? Ra parallel Rb must be very, very large. Now, does that affect your operating point? Can you make, in other words, can you make Ra parallel Rb very, very large without affecting your operating point? Yes, because the operating point is only governed by the ratio of Ra and Rb. Okay? Right? So the absolute impedance of Ra and Rb is still under our control. So in the topology in the top left, for example, if one chose Ra parallel Rb to be much greater than Rs, then the incremental value of the voltage at X will be the same as Vs. Okay. Now can somebody make a comment, similar comment for the here the gain will always be less than 1. You understand? Okay. And as I said, there is a practical difficulty of DC current flowing through the source, so it's not quite as preferable as the one on top. Okay? Great. So now that you've told me already what the incremental voltage at Vx is, can somebody tell me what the incremental voltage at the drain is? Let me call this incremental voltage Vout. Please note that all these small letters stand for incremental voltages. Okay? And to find the absolute potential at a node, you have to always add the quiescent value to the incremental value. So the incremental value Vout is what? In terms of Vx, what is it? It's minus Gm RL Vx, and Gm can be found because you already know the operating point. You can use any one of those many formulae that we derived for Gm, given bias current and W by L and all this other stuff. And Vx is approximately equal to Vs, which means that the incremental gain is minus Gm RL. There is still a small issue which we will, if the source can complain that no DC current should flow through me, it's quite fair to say that the load also can complain that there should be no quiescent current through the load. Here you can see that there is a quiescent DC current through the load. Does everybody see it? Okay. The quiescent current of the MOSFET is also flowing through the load. There are many loads. For example, the loudspeaker is one such, where if you have DC current through the loudspeaker, what will happen is it will go and saturate the magnetic core, and bad things can happen. So it is usually not a good practice to have DC current through some loads. Okay. So in other words, we need to figure out how to get avoid DC current flowing through the load. So any suggestions on what I can do? You can add a capacitor. Okay, a more systematic way of deriving this would be the following, which I'd say, this is RL1, okay. I'd say I'll dumbly connect this here. What is the problem with this? Is there any quiescent current flowing through RL1? Yes. Okay, so that doesn't solve our problem. And so if you want to avoid quiescent current flowing through RL1, what do? You can go through the same argument we went through with the source, which is you can add a battery here whose value is VDS1, okay, and then now the current flowing through RL1, the DC current flowing through RL1 is 0. Let's say the quiescent voltage between the drain and source is VDS1. If I added a load resistor RL1 directly to the drain, obviously there will be some DC current through RL1. However, instead of connecting it directly, if I connected it in series with a battery whose value is exactly equal to VDS1, then the potential difference between the two terminals of this resistor is what? Is 0. Because this is VDS1, this is the battery I postulate to be exactly equal to VDS1. So the difference between the two is 0. Okay? So there will be no quiescent current through RL1. Alright? And now you're all experts with batteries and capacitors, so what do? You replace the battery with an infinite capacitor. So now what is the incremental gain from node X to, let me call this V out now. Okay, let's draw the incremental circuit. Vs, what about Rs, is that there or not, is it gone? What about the infinite capacitor? There or gone? Short, very good, okay. Then what happens to RB? It is there. What about RA? We note that RA connects between this node X and to VDD. VDD is a battery, so for incremental signals it must be ground. So this can be simply replaced by RB parallel RA. That goes to the gate of the transistor. The incremental model for the transistor in saturation is simply, if this was Vx, this is GM Vx. Okay. Then what happens to RL? RL will go from the drain of the transistor to VDD. VDD is ground, so this is RL. Okay. What about the infinite capacitor in the drain circuit? It's a short. And what about RL1? Goes to ground. So in other words, the equivalent load is RL parallel RL1. This is the incremental V out. So V out by Vs, what is it now? Minus Gm into RL parallel RL1 divided by, into times RB parallel RA by RB parallel RA plus Rs. And by making a clean choice, in other words, if you chose RB parallel RA to be much larger than Rs, then the gain will approximately be minus Gm times RL parallel RL1. So this completes our very first amplifier. The source is common to both the input circuit as well as the output circuit. So if you look into the textbooks, this is what is called the common source amplifier. And the most important thing is that we have derived this completely from scratch without making any assumptions whatsoever. And you know why every single element is there in that circuit. If you pick up a textbook, what typically happens is that they present the circuit and then you write the equations and then figure out it works. You are often left wondering how the circuit came in the first place. And unless you understand the why of things, or the what of things, you can find from Google or from a textbook. That's not important. Okay? That's all information that you can get anywhere. You'll only be able to design and make things work if you understand why things are the way they are. Which is why I spent, 9 lectures deriving this, whereas I could have put this down on the board the very first day. And then a couple of things I wanted to mention regarding the transistor. Y12 equal to 0. And we've said that it turns out that the MOSFET, the device guys have cooked up a device where Y12 is actually 0 for all, regardless of what VGS and VDS you apply. So what does it mean physically? Y12 being 0 means what? If Y12 is 0, all that it basically means is that the output has got no effect on the input. Okay, so while it is true that the equation for the MOSFET is ID equal to 1/2 mu n Cox W by L, VGS minus VT, the whole square. This is an equation, right? Given ID, you will be able to find VGS, and given VGS, you will be able to find ID. But physically, which is the cause and which is the effect? Please note, this is an extremely important thing. VGS is the cause and ID, the drain current, is the effect. Let's assume VDD is sufficiently high, and let's say I put some VGS1 here. The ammeter will read some current ID. Now, if I took a current source of value ID and put a voltmeter here, what do you think the voltmeter will read? Do people understand the question? In the first experiment shown towards the left, which is this chap here, I take a battery of value VGS1. I apply it between the gate and source of a MOSFET. In the drain, I hook up an ammeter in series and connect the ammeter to a very large voltage VDD. What is the drain potential? An ideal ammeter should have no voltage drop across it. Great. Okay. So, and how will you find IE? The VGS is known, the dimensions of the transistor, W, mu, n, Cox, all that are known. So how will you find ID? 1/2 mu, n, Cox, W, blah, blah, blah. Okay. The second experiment shown here now, I take the exact value of ID which I had got in the first experiment, somehow managed to hook up a current source of the same value, and I pump it into the drain of a transistor. These two transistors are identical. And I put a voltmeter in between the gate and the source of the transistor. So my question is, does any of you or do all of you have any comment regarding what the reading on the voltmeter will be? 0. Why 0? I don't know why. What is so special about 0? I don't understand. Okay, then somebody says it can be anything. Obviously, there is something special about anything because anything can be anything. I would say ID is 1/2 mu n Cox W by L, VGS minus VT the whole square. VGS1 results in ID. So, I will make the argument that if I pump ID into the drain, I should get VGS1 at the gate. What is wrong with that argument? So, as I said, this is an extremely important point, and that is that VGS is the cause and ID is the effect. And just because you try and pump ID into the transistor doesn't mean that VGS will magically develop at the gate. The voltage can be anything. The voltmeter, you can't say anything about what the voltmeter reads, because 0 is as good a number as, you understand? Slightly unpalatable analogy. This is unforgettable. This is what I got taught and I never forgot, which was, you have a lot of food, you go to the bathroom, doesn't mean you go to the bathroom and food will come out from the other side. Okay? You understand? So, I think that analogy drives home the point. What is the cause and what is the effect? Okay? This is what cause and effect means. Okay, and this is what it means when I say Y12 is 0. You cannot force current through the drain of a MOSFET and assume that some VGS will magically develop between the gate and the source. You won't be able to predict that by looking at the equation. I will also point that out. This is coming because of the physics of the device. So let's get a little deeper into the common source amplifier and figure out what all there is to be figured out about this. If RA parallel RB is much greater than RS, then the incremental voltage at the gate is basically Vs. What is the absolute potential at the gate? So the absolute potential at the gate is VGS1 plus Vs, where VGS1 is VDD times RB by RB plus RB. The absolute potential at the drain is what? The quiescent value plus the incremental value. The quiescent value is given by VDS1. The incremental value is given by, which is, in terms of Vs, what is it? Minus Gm times RL parallel RL1 times Vs. So let's now plot versus time Vs. Let's assume Vs is a sine wave. Okay. So if Vs is a sine wave, the absolute potential at the gate is given by, so what is, let the amplitude of the sine wave be Va. So this is Va, and this is riding over a DC value which is equal to VGS1. The drain potential is riding over a DC value of VDS1. Okay, can somebody tell me how the waveform will look like? And what can you say about the amplitude of the sine wave at the output versus the input? Hopefully you've designed these things such that the gain is reasonable. So let me just draw a larger sine wave there. And the amplitude you see here is Gm RL parallel RL1 times Va. Take for argument's sake, Gm RL parallel RL1 is, let's say, 10. So if I put 1 millivolt at the input, at the output, if I measure the amplitude of the swing, it will be 10 millivolts. Okay. Then I put, say, 10 millivolts at the input, I will get 100 millivolts. If I swing 100 millivolts at the input, I will get 1 volt. If I put 1 volt at the input, so clearly this has to stop somewhere. So the next obvious question is, where does this stop? Let's try and figure that out now. So when do you think you will get incremental gain? What all conditions need to be satisfied to get incremental gain? Small signal, okay. What else? When a MOS transistor is giving you gain, it is operating in the dash region, saturation region. Okay. So now if I go on cranking up VA more and more and more, this waveform here is the absolute voltage at the drain. Oh, please note, what is the absolute voltage at the output here across RL1? What is the DC potential at Vout? 0. So the absolute potential at Vout is the same as the incremental potential, right? And that is simply GMRL parallel RL1 times VA. And I mean that makes sense because this guy here is simply a battery of value VDS1 and this quiescent potential is VDS1. So the waveform here will be riding over a DC value of VDS1. The waveform at Vout will be riding over a DC value of 0. So the waveform in red here shows the absolute potential of the drain. Similarly, the waveform in black shown below shows that's the absolute potential of the gate. Okay. So as the input voltage increases, as the source voltage increases, do you think the transistor is getting out of saturation or getting into saturation? I mean, is it moving deeper into saturation or moving out of the saturation region? What is the definition of saturation? What defines the limit of the saturation region? So the limit of saturation is defined by VDS being exactly equal to VGS minus VT defines the limit of the saturation region. In other words, the drain can go below the gate, but it cannot go below the gate by more than one threshold voltage. That's an easier way of remembering. So in other words, if the drain is coming closer to the gate in potential, is the transistor going deeper into saturation or trying to go out of saturation? It is trying to go out of saturation. Okay? So in the first half of the cycle, do you see the drain coming closer to the gate or going away from the gate? The drain potential is coming down, the gate potential is going up. So what does this mean? The transistor is being pulled towards out of saturation, which is coming towards the which region? Towards the triode region. Does it make sense? So in the first half of the cycle, the transistor is being pulled towards the triode region. Okay? So now it seems clear that it's only a matter of amplitude. Okay, if I put in for this particular value of VA, these are the output waveforms. If I doubled or made VA 10 times, for example, what would happen? If I made VA larger and larger and larger, what would happen? Pardon? If I made VA, for example, do you see the point now? So if I increase VA, the drain is coming down, which basically means that the drain and gate are coming close together in potential. In other words, the drain is trying to go below the gate. Okay? Alright. And it seems clear that it's only a matter of increasing VA. Eventually the drain will definitely go one value, 1 VT below the gate. To drive home the point, if I now get greedy and increase the swing to a much larger value, what do you think will happen to the drain waveform? So the drain waveform will do the following, which is actually I should have drawn it 10 times larger, right? So which would have. So the key point basically is to understand that these two are equal to GM times RL parallel RL1 times VA. Now can you tell me what is the maximum value of VA I can put in and still avoid the transistor getting into the triode region? It is at this point in time that the difference between the drain and the gate is the maximum. Correct? And that is the point in time at which the drain is going below the gate by the largest potential. Okay, so it's at that point that you have to worry about things. How large can this be before the transistor gets into the triode region? So what did we conclude that day? We concluded that the transistor will be just at the edge of saturation provided the drain is one threshold below the gate. The black waveform is the gate waveform, the red waveform is the drain waveform. And the drain clearly is going below the gate at this time. And to just to reach the edge of saturation region, this distance or this voltage difference can at most be VT. Alright, so using geometry, what can you tell me? So what are we trying to solve here? This is what we are trying to do. Okay, we realize that when the input amplitude is very small, everything is hunky-dory, right? No problem. And as I go on increasing VA, the gate amplitude is increasing, the drain amplitude is also increasing. The amplitude at the drain is going to increase at a much larger rate than the amplitude at the gate, because simply this is an amplifier. And physically you can see that if I go on cranking up VA, there will eventually be a value of VA that will drive the transistor out of the saturation region and move it into triode. What I am trying to find is how large this VA is. How do I figure this out? So VDS1 minus GM RL parallel RL1 times VA is the lowest point in the red sine wave. Okay, so that is that's this guy there. Okay, and that must be equal to, what is the topmost point on the black sine wave? VGS1 plus VA minus, alright, VA max is given by what now? It's now quite straightforward. It's VDS algebra, VDS minus VDS1 minus, actually this is VGS1 plus VT by 1 plus GM RL parallel RL1. So as long as the amplitude of the input sine wave does not exceed this VA max, you can be assured that the transistor will remain in the active region during the positive half of this cycle. Does that make sense? Please note that it's only during the positive half that in the positive half of the input cycle, the gate is going up, the drain is coming down. So the transistor is going towards the triode region. Okay? And eventually, as we saw, you can go on, if you went on increasing VA, you will always hit a point where the transistor enters the triode region. This VA max is the maximum amplitude of the input sine wave that you can sustain without the transistor getting into the triode. Does that make sense? Okay, what happens in the negative half of the cycle? No problem. Let us see. Now that you are all experts with incremental analysis, can somebody tell me what the drain current of the transistor is? In any nonlinear network, the total quantity is the sum of the quiescent quantity plus the incremental quantity, where the quantity is either voltage or current. So if I am interested in finding the drain current of the MOSFET, to be more specific, if I am interested in finding the total drain current through the MOSFET, I should basically be doing what? What should I be doing to find the total drain current in the MOSFET? Drain current is the quiescent value. What is the quiescent value? ID. And ID can be found because we know VGS1 already and we know the details of the transistor. So the drain current of the MOSFET is the quiescent current ID plus the incremental current. So what is the incremental current in the MOSFET? What is incremental drain current? It is ID, and is it flowing in the same direction or is it flowing in the opposite direction? It is flowing in the same direction. So the incremental current is nothing but GMVS. And GMVS is valid provided RA parallel RB is much larger than RS. So this is the incremental current. Positive half of the cycle in input sine wave, what is happening to the MOSFET current? So during the positive half of the cycle, the absolute current in the MOSFET is, the drain current to the MOSFET is increasing. What happens in the negative half of the cycle? ID is decreasing. Okay, so just like in the first case, if I got greedier and greedier and greedier and went on increasing VA, what would happen? I mean, we already have seen what will happen during the to the drain source voltage during the positive half of the cycle. Now during the negative half of the cycle, so let me just plot during the negative half of the cycle. So this is again VA, this is VGS1. This waveform on the top, what I want to plot is the drain current of the MOSFET. It will be riding over an average value of ID. Okay, it's the quiescent value plus the incremental value. The incremental value is a sine wave. So it should be doing. So is this ID in phase with Vs or out of phase with Vs? It's in phase with Vs. So it will do this. This is ID. And what is the amplitude here? GM VA. What do you notice as I go on increasing VA? What do you think will happen? I mean, during the positive half of the cycle, ID is increasing. It will go to a maximum value of GM ID plus GM VA. In the negative half of the cycle, what do you think is happening to the drain current? ID minus GM VA. So if I go on increasing VA, what happens? So eventually, if I go on increasing VA, I will definitely end up in a situation where the absolute current goes to 0. And now what is so special about 0? The transconductance of the MOSFET depends on ID, correct? It's square root 2 mu n blah 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 proportional to square root of I. And as the input signal is varying, the quiescent current, total current of the MOSFET is also varying. And if the input amplitude becomes too large, on the positive side, you will end up with the transistor trying to get into the triode region. On the negative cycle, what will happen is that the drain current will actually tend to go to, if the amplitude is sufficiently large, the drain current can go to 0. And if the drain current is 0, what is the transconductance of the MOSFET? The transconductance of the MOSFET is 0. Okay, in other words, the MOSFET is dead. So what is the maximum value of input voltage you can apply before the transistor gets, there's a term for this, it's called cutoff. Okay, so here ID equal to 0, which means the transistor is cut off. And what is that limit? What is the limit? How large can VA be while still avoiding the condition ID equal to 0? ID must be equal to GM VA. So ID by GM can be, let me call this VA max 2 and let me call the earlier one VA max 1. So the obvious question is, what will happen if the current is if VA is larger than VA max 2? What do you think will happen? Let's kind of physically understand how this amplifier is working, okay? Before the signals are applied, there is some quiescent current flowing through the drain. Okay, the current, so if Vs was positive, for example, then what is happening to the quiescent to the current through the drain of the transistor? The current through the drain is increasing, which basically means that if the current is increasing, that must come from somewhere else, isn't it? And where is it coming from? Partly from RL and partly from RL1.